It's your thing. So it's a pleasure to introduce Lucas Gabriel de Amorin. He's going to speak about that. He's from Buenos Aires. He's visiting these days Ángel González Prieto, so it's a pleasure that you decided to visit us, to visit Complutense. As well, he was giving also some other talks in ICMAT and other places, so it's a great pleasure to have you here. He's going to talk about Motivic mirror symmetry for character stars. Thank you.
Okay. So, thank you for the invitation. And so let me start. Just to be all in the same page, let me define what's a character varieties. I think all of you know what it is, but okay. So we have some surface of G, so something like this, and some market point. And we are going to pick some complex reductive group and some controversy class inside G. Okay. And the parabolic variety is this set of local systems over the surface of the point, which has some Q monodromy around the point. So explicitly, it's some morphism from the fundamental group of the variety without point to G that maps a small loop around the point to some fixed controversy class. Okay, and we quantify the action of G by conjugation of inside. The fundamental group, we know what it is, so this is given by an explicit equation, which we have two G elements on G, such as this product of its commutators belongs to C. And you might see there is a small circle here, and that means that we are going to take actually a connected component of this. Not exactly a connected component in general, but we need to take, so you lift your controversy class to the universal covering, so choose one leaf of that controversy class. You look to solutions of this equation into universal covering, and then you quantify by the fundamental group. So that is in general just a connected component of this space. Okay. So we have this space. But our motivation to study this variety actually comes from another place, which is Higgs bundles. So probably also you know what a Higgs bundle is, but just let me tell you the definition. So a Higgs bundle is just a vector bundle together with some morphisms. But instead of going from B to B, that's just a matrix over every point, we have a matrix whose coefficients are now one form. Okay, so it's some twisted endomorphism. We have a notion also for G, which changed vector bundle but principal bundles, and now the one forms have coefficients on the algebra of G. And well, there is also a parabolic version, which is a little more complicated, but there is some version, and there are more spaces. And a famous theorem of Simpson is that the character varieties and these dot-catcher model spaces are dot-ball model spaces are diffeomorphic. Okay, so we are going to speak a little about the dot-ball model space and then go back to character varieties. So there is a configuration for the dot-ball model space, which is the teaching configuration, and it's just given by the characteristic polynomial of the matrix. So we have some vector bundle with a matrix at every point, which is this twisted endomorphisms, and we can take the characteristic polynomial. That's some polynomial that if we have a matrix with real coefficients, it's just a polynomial, but if we have one forms, this matrix now have some forms as coefficients. So this is defined for the to some space of forms on the group. Okay. And a theorem of Hitchin is that this map is proper and is a complete integral system in the sense of symplectic geometry. Okay. And even more, the fibers are usually Jacobian or certain curves, and in particular are abelian varieties. Okay. So now let's G dual with the Lagrange dual group to G. So I'm not going to define what that means, but you think about you take SLN, the Lagrange dual is PGLN, for example. So when you take these two groups, it runs at the Hitchin configurations, fibers over the same space. Okay, so the same space. And what has been proved by Hausel and Thaddeus, in the case of SLN and PGLN, is that the fibers are dual abelian varieties, the generic fibers. And in the case of general G, this is the theorem also by Donaldi and Pantet, some restriction on the conjugacy case, but never mind. So we have this situation where we have two varieties, some which fire over the same base, which generic fires are dual abelian varieties. This situation is actually what Sturming, Yao, and Sadlow proposed for mirror symmetry. Okay, so in the sense of say, this should be two varieties we are symmetric. Okay, and of course this kind of a geometric mirror symmetry, and one expect to see this symmetry in other invariants. And in particular, Hausel and Thaddeus make a specific proposal of what this symmetry would look like in cohomology, a level of Hodge numbers. There is an issue here is that the generic fires are dual abelian varieties, but there are some fires which are singular. Okay, maybe not reduced or whatever. So, what there has to be some corrections to just not say the Hodge numbers are the same, but there is some correction, and this is given by the orbital cohomology, also called stingy cohomology. And I'm going to define it just in the case of this very specific case where we have some finite abelian group acting on some symplectic variety, preserving the symmetric form. Yeah.
Ask one question. Sure. What is your C there?
Let's see. So this is the concurrency class we are fixing.
Okay.
Okay. So in this theorem, C is either trivial or, in the case of GLn and GLn, center of binomial.
Okay.
So in this case, we are going to have, so I will give you only the definition on this case, which we have some finite abelian group acting on some symplectic variety, preserving the symplectic form. And so the idea is that if say X is simply connected and gamma acts freely, okay? So in the quotient, then you know that the fundamental group is gamma. Yeah. But now, how you prove that? So essentially, what you do is you take some point X, you take some other point directing by gamma, you take some loop, and then some path, whatever path, in the quotient, you see some loop. Okay. Now, when the action is no longer free, you start to lose these loops because these points collapse and you lose. Okay. So essentially, you get something which is contracted. So the idea of this orbital cohomology is in some sense to recover these loops you are losing, okay? And so one looks to the Fiesel points, okay, which are these pairs such are you no longer have these loops, okay? So we have this set of Fiesel points. And orbital cohomology is just taking the direct sum of all cohomologies of the Fiesel point sets up to some shifts. We have the codimensions of the Fiesel points. This is a rational cohomology in the sense it has some cap product, some functional duality, a mixed structure, and so on. And for example, the mixed structure is just taking the mixed structure for each y, and you simply add them and make the shift. So that's something you can do. In particular, we can talk about stringy Hodge numbers, okay? Which are just take the Hodge number of these guys, make some shift, and whatever. So this is the conjecture by Hausel and Thaddeus, okay? So the conjecture is that we should take the model space of Higgs bundle for SLN, we look at the model space for Higgs bundles for GLn, look at the stringy Hodge numbers, then there has to be an equality, okay? As long as we take some conjugacy class of central order combined with them. Okay? So this is the conjecture. And this has been proved, and actually in greater generality. So for example, there is a proof by Grotzenick with Ziegler using Gaussian integration, where the proof is for essentially whatever kind of situation of these Sturming layouts are allowed, okay? With some additional hypotheses, intersingularities, and whatsoever. There is also a proof by Mollick and Chen, which is relative to the base, so with the base of the population. And there are generalizations at level of choke motifs. So what was the motifs? One by Dosser and Weiss, which use Motivic integration, and the one of Hausel and M, essentially is use Mollick and Chen ideas. Okay. But this is now too hard. So our question was whether this symmetry is also true at the level of character varieties. Okay. And so we first do some computations with Mellit. And it turns that you can prove for finite quotas on SLN that it is true. Okay. So if you take, this is the theorem, so if you take the character variety for SLN, some finite quotient, say by CD, and you look to its Langlands dual, which is again a finite quotient of SLN, but now you quote by Cn over D. Okay. Then the string Hodge numbers agree, as long as you take some constancy class which is regular and symmetric. Okay. Actually generic. Yeah, it's not only regular and symmetric. Well, we actually use something more explicit, and we just compute the polynomial, which is this generic function. Okay. It has some formula like this, so it doesn't matter what this formula says, so it's something that you can compute. But the important thing is that you can check that this is symmetric on n and on D and n over D. And in particular, you have this symmetry. Okay. And well, the way we prove this is essentially an approach which is known, which is you go over finite fields, you count pointers within character theory, and you go back to the complex number. Okay. And in particular, this doesn't tell you anything about the geometry or why this is going on. Okay. And in particular, on the character variety side, you don't have a hitching base, you don't have a hitching vibration. So there is actually no geometric meaning of this equality. Okay. So we would like to have some more geometric proof of why this holds. Okay. Yeah.
Why the role of D and D prime? What's the idea of the? Why do you take one quotient on the left hand side and a different one?
Yeah, because
what's the motivation of?
Well, you want to look at the Langlands dual group.
Mm-hmm.
Okay. And the Langlands dual to this group is this other one. So essentially, Langlands dual change fundamental groups by center.
Mm-hmm.
So in this case, this guy has fundamental group over D, and its center has order n over D. In this case, it's the other way around. Okay.
And both of them, one of them should be even, no? Otherwise, you would have in the formula n squared divided by 2. That wouldn't be right.
No, but I think this polynomials compensate this over 2. It turns to be a polynomial. So, okay, so this is like the theorem, and we would like to have some more geometric explanation, and so we go to the Grothendieck of arbitrary varieties, so to look to some Motivic version of this. So let me remind the definition of this, probably you also know it. So we have isomorphism classes of varieties, we look to the abelian group, really abelian group divided by 10, and we have these relationships with like the class of some variety is going to be the same as the class of an open set plus its complement. Okay. And this is what we call the K0 varieties. And it has a product, so it's a ring which is given by the product of varieties. Okay. And the motif of some variety is issues its class on this ring. Okay. So we want to do some conjecture at the level of this ring, and particularly this recover the polynomial. But for that, I need to tell you what the stringy motif is. So now I'm going to give you the vision in the same case that before. So we have some finite abelian group acting on some symplectic variety, and the stringy motif is going to be the stringy motif of the pixel points plus some shifts. that are given by the other measure. Okay, so it's the same formula than before. This is just to match what happens at level of counting points and at level of the string point. Okay, here Q is just the class of the print line. And so the conjecture we have is that this equality at level of Hodge numbers actually lead to the Grothendieck release of varieties. So it's the conjecture that we have some connected symmetry group and LG is Langlands dual group. Then the stringy motifs of character variety for G and the character variety for Langlands dual G agree as long as we take generic conjugacy classes. Okay. So this is the conjecture. What's the meaning of the conjecture? So I'll tell you, like, we wanted to have some more geometric meaning. Well, the meaning of that is that in some sense you can take the character variety of G, put it on certain pieces, glue it back together, and get the character variety for Langlands dual. Okay, but of course we need some stringy corrections. And so what I want to talk about now is how to cut the character variety for G. Okay, so one can cut this variety. So what is just remember, like, this was the definition of the character variety. So we have some tuples of brackets, and now before we ask it to belong to the conjugacy class, that's the same thing of asking times some line in the conjugacy class is equals to 1. So it's exactly the same. And now we need some different versions of the character variety, and for that we're going to take some Borel subgroup of G. Let's U its unipotent radical, and let T be some maximal terms only. Okay. So if we are working with a generic conjugacy class, in particular it has to be semi-simple, so we can choose an element that's association with the terms. And we can define this tilde character variety, which essentially is very similar to the previous one, where it has two differences. On one side, the C that was varying along all the conjugacy class, we are going to fix it to be C. So in particular, we can no longer code it by G because the equation is not longer G invariant, but we have to code it by the centralizer of C. That if we are working with a genetic conjugacy class, that's just T. So we code it now by T, not by G. And in addition, instead of asking to be equals to 1, we are going to ask to belong to the unipotent group. Okay. So in the case of GLn, this is an upper triangular matrix. Okay? So this product of it will be an upper triangular matrix in the case of GLn. So we have this tilde variety. And the theorem that for GLn is of Anton Mellit, and the general G is for myself, is that if one has some connected utility groups and some generic conjugacy class, then this tilde character variety can be cut in some pieces, which looks like finite quotients of some affine spaces and some torus. Okay. So I want to talk about a little about the proof of the theorem. Okay. To give you an idea of how to put it. Okay. So the first step is to write this tilde variety in some better way. Okay. And for that, we need the notion of a D variety over G. That's just a variety over G. So it's a variety with a morphism to G. That also has a T action. Okay. And the action and the morphisms are compatible in the sense that if one acts and then applies the function, it's the same thing of applying the function and then making a consideration by T. Okay. An example of that is the commutator. So we have G by G as a variety, G times G as a variety, and the commutator map. Since the commutator takes conjugations into outside, then this is a T variety. Okay. So and let's call it K, it's gonna be a few times. So also there is some convolution of T varieties over G, which is just given by the product of varieties, the product action, and the morphism to G is taking the morphisms of each component and then multiplication of G. And there is an operation of taking fiber, so whatever element you choose, you can take fiber. If it happens that you take an element which is T invariant, then the fiber is also a T variety. Not only a variety, but will inherit action of T. In particular, at the neutral element, we have some T variety. Okay. So what turns to call is that if the still a character variety can be written as some convolution of this guy K with unit patterns times the element we fit C. Then we take the fiber over the entity, and then we code it by T. Okay, this turns to call. Okay. So now the problem of understand this variety turns to be the same of understanding first the convolution with K, then understand how to take fiber, and then understand how to code it. Okay, so that's the three things one has to do. So for the convolution, what we are going to do is to use Lucas decomposition. Okay, so let W is the bigroup of G. Okay. So the Lucas decomposition is this decomposition. So essentially, G can be written as some disjunct on the elements of the bigroup, where each cell is BWB. So this is well defined because inside P there is some T, so we are taking out the quotient associated, the coset associated with those. So we have this decomposition for G, and K was a product of G times G, so we can decompose K as some products of two hat cells. Okay. And so what we need to do is to compute the convolution of U against some products of the hat cells. Okay, where this is a law with the commutator map to G. Okay. So to compute these convolutions, we need some notation. So it's a notation. So then alpha we are root by G. So whatever root. And given a root, you always have an SL2 subalgebra for G. And by exponentiation, you get a morphism from SL2 to G. Okay, so an embedding of SL2, but maybe not as an embedding, but some math. And so we can associate the following morphism to the root, which is given by taking some complex number, do that matrix, and then apply the inclusion. Okay, so that's something we can do. And now by convolution, you can speak about take whatever word on the roots, and you get some element, some variety of a G. Okay, just by convolution, these elements. And now, in particular, if you take the bigroup is generated by some symmetries associated to the roots. Okay, in particular for the simple ones. And so you take your W to take your favorite element of W, you write it in some minimal way in terms of these symmetries. That gives you a word, and that word gives you some variety over G. That variety, call it FW. Okay. So of course there is some choices there, but just call it FW and forget about the choices. So what this is shown is that if you want to do the convolution of this product of Lucas cells against U, what you take is U convolution. Some point convolution. Some tori, which are here by commutators against W's, and then some of this F with in some word. Okay, so this is the word which looks like a commutator. Okay, so this is what is shown. So why this is useful? Well, now the problem is to take some first the convolutions, then take fiber, and then quotient. So now what we need to do is to take fiber of this kind of variables. Okay, and there are more simple steps. They mention also that this formula can be inducted. Okay, so notice that U here is at the very right, and now here is at the very left. So you take another Lucas cell, another product of Lucas cell, and try to do the convolution. Then you first do the convolution with U, and then you have Lucas cell convolution with U, so you can do again the formula. Okay, so it can be inducted. So we need to compute these kind of things, which are fibers of convolutions of U against some F of some word. Okay. Now, so there is the following observation that is taking the fiber means taking equals to 1. So it's saying we have some element of U, some element on C. We take U times FW on C, and that has to be equals to 1. Now you can take U to the other side, of the equality, and now you can rewrite the equation of FWC belonging to U. Okay. So we need to describe these sets equivalent. Okay. So to describe these sets, we are going to use again the Lucas decomposition. So the problem is as follows. So you want to take whatever FW belongs of C belongs to U times C inverse, and then you can think about it first belong to B, which includes U times C, and then to B actually of the form U times C. Okay. So for the belonging to B, we are going to this sequence of elements on W, which you remember these FWs on some C, if W is equal to some 1, we choose something like this. Is of the form, okay? So instead of asking choose to this belongs to me, we are going to look to partial products and act in whatever blue hat cell they are like. Okay, so we look to these partial products. Well, it has to belong to some blue hat cell. Let's call the blue hat cell associated to some PK. Okay, so for each vector on the finite space, we have some associated sequence of elements of W. Okay, and we want to sequence such that PL is trivial. Okay, that means to belong to the Borel at the end of the day. So, in addition, each blue hat cell has a projection over the toroid. Okay, so each blue hat cell looks like some products of the finite spaces and the toroid, and so you can forget the finite space and get something on the time. Okay, so now if U, so to belong to U times C inverse, when you know it belongs to B, means that over the associated map, you end up at C inverse. Okay, so you can rewrite this space you want to understand as a return union over two possible bits P, so over two possible sequence, and end up at the trivial element, and you take the identifier by C inverse. Okay, so you need to understand this kind of stuff. So to describe the possibility piece, we need what's called the blue hat concept. So I'm going to define it using an example. So let's check the SL3, the suppose. And so in SL3, there are only two simple loops called alpha, let's call it alpha and beta. And the back loop is the symmetry group on 3 elements, which have 6 elements. So the blue hat concept we have as elements or possible elements in the pi group, and they will be ordered by what's the minimal number of symmetries on these roots you need to break them. Okay, so for example, in SL3, you have at the very bottom 1, which is writing with 0 symmetries, then the both symmetries, then you have the product of the 2 symmetries, and then the 3 products, which are in this case equal. Okay. And now there are going to be arrows in this graph that are given. So if one can go from some W to some other W prime, by multiplying at the left by some symmetry, you put some arrow. For example, you can go from 1 to the symmetry associated to alpha multiplied by the symmetry associated to alpha. Okay, and we are going to put them some label. We are going to label it with the symmetry while multiplying. Okay. We can also go to the symmetry associated to beta, and from 1. And now, if we are as alpha, we can either go with multiply by the symmetry associated to alpha and go 1 to 1, or we can multiply by the symmetry associated to beta and go 1 and go then up to this other end, and so on. Okay, so from S beta, you can go to S alpha S beta and other. Okay, so you have this kind of graph. And notice that for every element, there is exactly as many edges either coming in or coming out as simpler roots. Okay, so for each root, you have either you go up or you go down. Okay. And so what happens is that you take some complex numbers on this vector, the complex numbers, and you see its associated sequence of p's. this cannot be of whatever form. We have to satisfy the following rules, okay? Which essentially say the following. So suppose you are like, so your PK is some S alpha, okay? Suppose you are there, and then it comes some root. So you have this. The following comes like some F alpha chi plus 1, and so there is two cases. So you look at the arrow here by F alpha chi plus 1, okay? So let's say it is beta. So if that arrow is going up, you have to follow it. So, okay, so if you are in S alpha and comes a beta, you have to follow it and go here. Otherwise, that arrow is going down, and then you can choose between either staying at the same element or going down to whatever the arrow is going. Okay, so if you are at S alpha, it comes on alpha, then you either choose to stay at S alpha or to go down to 1. Okay. So this is kind of the rule. It has to follow this P. Okay, and we are going to call walks to sequence that satisfies rules. Okay, and so these are the possible sequence. And so let pick a sequence and let UP be the places where we go up and SP the places where we stay. So what is shown is that the set of possible, so you look at 2C that have the specific wall, so the associated sequence on W with this specific P, and this set looks like this, so it's applied to finite space and some torque. And essentially it has to do with, if you're going up, you always have to go up. So it doesn't matter which C you're multiplying them. So that's why you have this C here for each going up. And now, in the case where you either choose to go down or to stay, what happens is that for a very specific C, for a unique one, you go down, and for the others, you stay. So that means that whenever time you choose to stay, you have some Q-1 options, and in other cases, you have only one. So that's why it is shown like this. Even more, one can compute that this projection on the tori has a very specific form, which is that one. That doesn't matter. Okay. So now we know what this set looks like, and we have to take the fibers. Okay. And so what happens is that if you take some of the sequence that finish at the bottom, then there is an equivalence between the morphosis of this projection of the tori from this cell, so you restrict to this cell. So from this cell to the tori, this map is going to be subjected if and only if the tori acts with finite stabilizers, put to the center that always are trivial. And so this means that if you take some contrast class was genetics of this C was generic enough, then the only GLs that give some non-trivial image, so non-MP image, for those GL, the tori acts trivial. They acts with finite stabilizers. And so you can prove using that the elements GL inverse of C we are looking at, quotient by T is either empty or a finite quotient of something at the form which is a finite space, some tori, and maybe some connected components. Okay. And so this proves that they give you the composition we wanted to have. Okay. So a finite quotient or a finite space is vector. So so in this way you stratify these varieties. Okay. So why this is useful for the conjecture? So the point is that you can simplify the conjecture. Okay, that's why I want to tell you now. So first, few notations. So the first point is that we were talking everything T equivariantly. Okay, but actually can be done B equivariantly and even more with some action of the center too. And so let's call for each possible P, CP, a connected component of this pre-image, this kind of triangle. And so we need to look at this string kind of stuff. And for the stringing, you need to look at fixed points, okay? But fixed points on the character variety, not on this tilde character variety. And what happens is that character variety is essentially a U quotient of the tilde character variety. So one needs to look pixel points up to the action of U. So the kind of pixel point one has to look is these guys, which are CP gamma, going to be the union of all pixel points associated to something of fun U times gamma. So this is answer. So it is shown that these are generically empty, but for some finite set of gamma, they might be non-empty. And the conjecture is that if you take some simply connected now, so you can just choose work with simply connected groups, same simple group, and you take some of these cells that are produced in the decomposition, then taking these pixel points, if they are not empty, then it compensates with the shift we were doing of the dimension. So the motif of the pixel point set times the shift is equals to traditional motif. Okay? And we proved that this conjecture actually implies the last one. So okay. So the conjecture implies the last one. And what is the point for this? So all of this decomposition, all of this index instead of the decomposition depends just on the bi-group, essentially. So the bi-group or how the algebra is, it doesn't really matter what is actually the group. In particular, if you check G by the Langlands dual, the group hypothesis is exactly the same. The words are exactly the same. So essentially, everything is the same. There is some small difference because the center changes by the fundamental group, but you can check that everything works well, and so this conjecture implies the previous one. Okay, and we check that this conjecture holds for SM2. Okay? We don't know it in general, but this one implies the previous one. Okay. ¿Cuánto tiempo tengo? En teoría hasta un punto. Okay, so this is like formal motivation. So in this work we have like this right idea, and now I want to talk now about another application, okay, which is work with Angel, Martin Havlicek from Leiden University, and Martin Mellit from Buenos Aires. So in this case, we are going to work with the handle operator for the TQFT, the confused representation variety. You might know maybe what is this, maybe not. And so this handle operator is something that goes from the quaternion of varieties over G to itself. And what we can prove, here this B shouldn't be there. So this B is erased. And so what we are able to prove is that for any element of the tori, this is a finite dimensional module of this ring, which is invariant of the handle operator. And that contains the class of U times C. Okay. So we are able to prove this. And essentially the proof is you follow like the previous algorithm to compute the handle operator. Okay. So why this is useful at all? This doesn't really very useful. So let me talk a little about induction. So induction is the following. So there is a map from, if you take some B variety over G, you can produce a G variety over G, which is given as follows. So you have your B variety, which is some variety and some map. And you're going to do this product, so you take product with G, and you quote it by the action of B, which is X on X by direction, and in G by right rotation. Okay. And the map is just given by the map of the X plus conjugation by the element of G. And what happens is that induction commutes with the handle operator. And so a corollary of the previous theorem is that if they any regular and semi-simple conjugacy class, then there is an invariant module under the handle operator that contains C and is of finite dimension. Okay. And essentially the proof of this is you take U times C for C something regular and you do induction, and that gives you the conjugacy class. So this is useful to compute the motif of the character varieties very explicitly. So that's useful for that. So let me give you some examples. So first, an example for SL2. So for SL2, you do the computations. You have 4 generators, which are, well, I will tell you it before induction because just the same. So before induction, they do like this. So you have U times C, you have the model subgroup of SL2, you have the other Bruchard cell, and you have one more element, which is a double cover of the Bruchard cell of B. Right? It's a double cover of B. And the handle operator can be computed very explicitly, it's here like this matrix. And so if you take this matrix and you analyze it and whatever, you can compute the motif of the character variety, which is given like this, which is a result of 1. So 1 recovers the result. In the case of a generic C, the result of function is for whatever C. And another example is PCL2. So in PCL2 now you have 3 generators, which are these ones. So you have U times C, you have the Borel subgroup of SL2, and you have the other Bruchard cell of SL2. You can also compute the handle. And doing the same thing, you recover now a result of caveat, which looks like this. Okay. And so that's it. So thank you very much.
Questions?
Yes. Okay. Yeah. I have many, but okay. Can you go to the simplified version where you?
Yeah.
There it is. Okay. There you decompose, and then you say this shows that it's empty for all but a finite set of gammas.
Yes.
Can you give me some intuition? I mean, why all the decomposition reduces to a finite set of those?
So in the case, say, of GLn of SLM, what happens is that when you quote it by T, that the T action is free, you quote it by E, and you get now just an action of the center, which is finite. So that's why we got this something finite. But for types B and C, the action of T is not longer free, but has finite stabilizers. So you have to put something which is inside the center plus whatever singularities you are having. So that's where it's finite.
Time for one more question.
Well, yes, I'm the expert, but there are many technical things. And then in the decomposition as convolution, you have some copies of SL2 into G, and they were of a very specific form.
Yes.
What's the intuition behind those maps that were crucial when you? I mean, you've got many ways to inject things, and then in the decomposition of. My question is, are they crucial the way they are, or is it simply a particular choice so that you have a decomposition that then you use and it works?
What is important is that you take some minimal writing of W,
Okay.
then FW convolution with U, it will give you some partial Lucas set. So this is kind of the main point. Of course, you can choose another set of simple roots, another model, and it also give you a decomposition, which is different, and give you combinatorically the same thing, but geometrically something kind of different. So there are some choices.
And is there any way to see to have a map from one to the other?
From one characteristic to the other one?
Yeah, I mean, when you change the word.
No.
You don't have any way of showing this deformation.
No. But so when you change the model, as you say, you change the Bruchard decomposition, but it looks the same. So each piece, so there's the same number of pieces. Each piece is just the same thing, but just like different embedding. But like there is no map.
So we have another seminar now, so we are cutting short today. So if you have any more questions, please contact the speaker. Also, if he allows me, I can upload the slides to the webpage, so you may have your version of this. And thanks to the speaker again for this wonderful talk.